presentation with Gyula Molnár, who is a second-year PhD student at the Pázmány Péter Catholic University in Budapest, and I'm a half supervisor because we are two with the Professor Mihály Kovács. And the division of the presentation will be
he's with the Technical University, isn't he?
Half-time
Yes.
and full-time with Pázmány.
I see.
So the first part will be my part, the overview of the problem and the preliminaries and the previous results and the motivations, and a recent publication will be described by Gyula, which is a specific problem. So in this part, he will show proofs and principles of proofs. Okay, so let us see the motivation. So why we are interested in kinetic models and chemical reaction networks. As a control engineer, this system class is interesting for me because the mathematical structure is ordered, friendly, but it can describe essentially any dynamics, which means that we can use computational tools for analysis and even for control design based on the system class. Why delayed systems? In many applications, the explicit modeling of time delay is absolutely necessary to describe some phenomena with a satisfactory level of precision. And this is not a new topic at all. So I just indicated two important papers. At the end of the presentation, there will be a list of references. So maybe this paper is the first or one of the first where delayed reaction networks are formally introduced with the motivations. And of course, there were important developments later, like this paper of Maja Mincheva and Russell. We know that complex balance and the corresponding nice properties like stability are very important in CRNT and beyond, I think. Here, please do not forget that complex balance is a realization property, which means that it's not a part or of the differential, or not the property of the differential equations, but the property of the CRN realization of the differential equations. And this notion is being extended. So this means that the properties can be applied for a much wider system class. And I think you heard in recent seminars about the disguised complex balance framework, for example, which clearly extend the scope of this analysis. I have to highlight the results of these Japanese authors, Komatsu and Nakajima, about the generalization of compatibility classes for the delayed case. Very important and nice persistence results, conditions for global stability under certain conditions, and this is the recent one, the analysis of time varying kinetics for delayed chemical reaction networks. And as I said, this framework or analysis might be interesting not only for CRNs, but for general non-negative delayed models, for example, through CRN realizations. Okay, let us run through the very standard notations. We have n species, m complexes. which are formally the non-negative integer linear combinations of the species. These alphas are the stoichiometric coefficients. We have R reactions in the network. So reaction means that some complex Ci is transformed to some other complex Cj in the network, and in this way we have a nice directed graph of the network. The reaction rate will be important. So here I just define the mass action case, because we will begin with the mass action case. So the reaction rates will be essentially monomial expressions depending on the stoichiometric coefficients, and we will use this power notation where this y is a vector. Okay, so from this we can write the differential equations of mass action type networks and other networks as well. So we will use this form summing along the reaction. So from the first reaction to the last reaction, we have the reaction rate, in this case a mass action type reaction rate, multiplied by the reaction vectors, which describe the production and the consumption of species in each reaction. So X will be the state vector, the concentration or abstract concentration vector. The complex vectors will be denoted by this K. R is the number of reactions. The reaction rate coefficient is kappa K, and I have already defined this notation, and we have a non-negative system, so the initial condition should be non-negative, or at least we are interested in the non-negative dynamics. The stoichiometric subspace is spanned by the stoichiometric vectors in this case, so this is a simple object, and in the mass action case it's also simple that we can define these first integrals where this A vector is perpendicular to the vectors of the stoichiometric subspace, and these conservations essentially define so-called positively invariant stoichiometric compatibility classes with the classical definition. A few words about complex balance, which is quite important. So you can see this kind of definition. This is also the usual, but the meaning is that at equilibrium, it's important, we have a Kirchhoff-like property in the network. So the signed sum of incoming and outgoing reaction rates is zero for each node of the network, so for each complex. In many cases, if there exists a complex balanced equilibrium, then any other positive equilibrium is complex balanced. We can give not very nice kinetics. I think there is an example in the 1972 Horn paper where this is not true. But in the cases that we are studying, this is always true. And the Lyapunov function corresponding to this complex balanced network is here. So this is just a simplification, this G notation. This is an entropy-like logarithmic Lyapunov function. And we know that the system is at least locally asymptotically stable on the stoichiometric compatibility classes, but most likely, according to the global attractor conjecture, this stability is global. And in a system theoretic sense, this is a very robust stability property, which is interesting not only for CRNs, but for any system that can be written in the form of CRN. The idea of the delays is not new, as I said, so we can assign different delays to the reactions or transitions in the case of compartmental systems, for example. And what can be the reason for a delay? Well, it's not, in most of the cases, it's not very chemical, we have to say. So for example, we do not want or cannot model a subsystem in detail. For example, a cascade or a more complex subnetwork. This can form some kind of delay formally. In a compartmental system, we can have transport delays. This is physical. And we can simply have a delay differential equation which has a kinetic realization, and this can give us a delayed CRN. So this is just a very simple compartmental example, a linear system. Basically, we have some compartments and transitions between the compartments, and some transitions, for example, this fourth transition and second transition are delayed for some reason, and this can give us a delayed kinetic model. So the first case studied in 2018, I think, is the case of a discrete delay. So the original equations, so these equations are modified such that the reactants are immediately consumed, but the products appear with some delay. So you can see this in this term, and the consequence is that you cannot factor the reaction vectors anymore generally in these equations. The notations are standard. I think there is nothing new in these notations, only that now we have an initial function instead of an initial condition. So back to some tau in time. A few words about the how we conjectured the first Lyapunov function for delayed CRNs, and this came basically from our uneducated nature, because engineers do not learn delayed dynamics, I think, most of the time. So what we can do, usually we approximate the delayed terms with some ordinary differential equations, and then we are happy that we can handle the ODEs. But the approximation is not arbitrary, so we used a physical based approximation of discrete delays given originally by Győri and Turi, and this was later extended to the vector case in the PhD thesis of Beata Krasnai. And this is the general form of the delayed differential equation. So the non-delayed part, the delayed part, x is a vector, but we have only one delay, this tau, and of course, so a more complicated function of the states can be delayed. This is the h function, and this delayed differential equation can be approximated essentially by a compartmental system. So we approximate the delay by a series of compartments from V1 to VL, and you can see that from V2 this is a linear subsystem, and in the first part we can have a nonlinear function. But from starting from this term, everything will be linear. And we can easily show that this approximation preserves the kinetic property. So if the original differential equation is kinetic, then the approximation will also be kinetic. And it also preserves complex balance, which means that we could generalize the stoichiometric compatibility classes and the logarithmic Lyapunov function. How? We wrote the logarithmic Lyapunov function as a sum of the functions of the state variables, and we just tried whether the sum, if we change the sum to an integral, so if the number of compartments goes to infinity, whether it will work as a Lyapunov-Krasovsky functional or not, and it worked. So this was the starting point, and that's from where we could generalize the notion of the stoichiometric compatibility classes. I cannot go into the details due to the lack of time, but now the compatibility classes are more abstract because now they are sets of initial functions. And if the delays are zero, then we simply get back the classical, the undelayed stoichiometric compatibility classes. And if we have the classes, then we can, as I said, we can develop the Lyapunov function or the Lyapunov-Krasovsky functional to study the stability of delayed networks. So this is the general form. You can see this depends on the initial. So we have n species and r reactions. So this sum is along the species. X bar are the components of the equilibrium, and this term is summed along the reactions. And again, this g function, just for the simplification of notation, is the same as before, this logarithmic function. An example for a discrete delay, very simple two-species network. One of the reaction is delayed, so this second reaction, and you can see that this is a reversible network. So we can write the delayed differential equation and compare the non-delayed notions and the delayed notions. So this red line is the set of equilibria, and we know that the set of equilibria are the same in the delayed and non-delayed cases. The green lines are the stoichiometric compatibility classes of the non-delayed system, and these black dashed lines are the compatibility classes corresponding to constant initial functions, because only in that case we can draw these lines for the delayed system. And you can see that the dynamics is qualitatively complicated a little bit. So these blue lines are the trajectories of the delayed system, but they are stable and the equilibria are the same, and we can prove with the logarithmic Lyapunov function the stability of the equilibria for arbitrary finite delays. Okay, so let's switch a little bit to distributed delays. So in reality, these delays are uncertain, or they have some distribution of arrival times, and the literature writes that distributed delays are much better suited for biological models. So the product formation now depends on a distributed delay, so an integral over past states, and weighted by a probability distribution. So this mu will be the distribution function, the d mu will be the probability density function. and the summing along the reactions is the same. And the result is essentially the same as for discrete delays, so the stability is preserved, and we could give a Lyapunov-Krasovsky functional to prove the stability for essentially arbitrary delay distributions. This is another example for the trajectories of a system of with distributed delays. A simple network again, one non-delayed reaction, one delayed reaction, and now these curved dashed black lines are the stoichiometric compatibility classes, and the trajectories are similar, so they are twisted, and the delay distribution in this case is very simple. It was a uniform delay over some interval. A next step was the consideration of non-mass action kinetics. Of course, a very well defined class of non-mass action kinetics. So these will be the reaction rates now defined by this gamma function. So this is a vector function defined element-wise, which means by coordinates functions. The the gamma I functions should have some important properties. So in a sense, this is a restriction. So they should be increasing and continuously differentiable. This property is evident, I think, and there are some, so the other properties are quite technical. Using this gamma, we can handle not only mass action kinetics, but for example, Michaelis-Menten kinetics or Hill kinetics. So essentially any rational kinetics. And the result is essentially the same. So a little bit more complicated, the Lyapunov-Krasovsky functional, but still works. And we could prove the stability for essentially arbitrary discrete delay in this case as well. This is another example. So the green is the delayed mass action case, and the blue is the delayed non-mass action case. So you can see the differential equations here, and you can see that the compatibility classes are now curved due to the non-mass action kinetics. So this is the summary of the findings. We know this, so this is nothing new, that the delays or the delayed system preserve the equilibria. This means that we can check complex balance in the same way as for non-delayed systems. This required a little work, extra work, the proof of the existence and the uniqueness of equilibria within each positive stoichiometric compatibility class. And this is physically maybe interesting, that these compatibility classes made us think about the redefinition of conservation, because we have some so-called material trapped in the delay, which has to be handled somehow. Okay, and at this point I give the floor to Gyula, and he will elaborate on the question whether the same nice stability properties are valid for non-mass action distributed delayed systems.
Okay, Gábor. Does that mean we can see it?
Can you get it off the frame?
Now it should work, right?
Your voice is very strange for me.
Is it? Okay. Okay, I know why. Just a sec.
Maybe now it's better.
Much better.
Yes.
Oh, great. Okay. I'm glad to hear that. Okay, so with that, thank you, Gábor. I would like to.
Can we get it off the frame, Gyula? Could you change the view?
Sure. Like this.
Not important.
Is this satisfactory?
Okay, we can see it.
Because I would like to take some notes on the slides. So, yeah. Okay, so I would continue from here then. As Gabor pointed out, we have had papers, not we, but there have been papers covering these three cases so far, when you had mass action kinetics with discrete delay, mass action kinetics with distributed delay, and non-mass action kinetics with discrete delay. And so the most recent work regarding this is basically filling the gap, whether these results hold for a non-mass action system with non-mass action kinetics and distributed delays. So for that, the general form of the ODE looks like this. So for gamma, we pre-assume, so this is basically a piecewise defined function that has to be C1 over the non-negative numbers, so continuously differentiable and also strictly increasing. And we also introduced to the ODE shown in teal here this distributed time delay, and this is a Stieltjes integral. And what's important here is this mu k function, that is the delay distribution itself. And the important property of the delay distribution is that taking its derivative, so taking its derivative is this function, and this has to integrate to 1, since this is this is a distribution function. This has to integrate to 1, and our three main results were equilibrium preservations, showing that the set of equilibria for this class of systems does not change with the introduction of the distributed time delay. The existence and uniqueness of equilibria in each stoichiometric compatibility class, and finally showing Lyapunov stability. And the first one, equilibrium preservation, that's kind of easy, so I'm just going to do this here in place. Basically, what happens is that if we have an equilibria, then it doesn't matter if we have t or t plus s here, because by definition this wouldn't change over time. So we just have a constant here, basically here as well. And because this is a constant, we can drop, because because we put the constant inside of this gamma function, that in turn will also be constant, and so we can just drop this whole expression or factor out this whole expression from the integral. And of course, this has to be 0 if we're looking for equilibria. And we have shown here that what remains is, because it's a Stieltjes integral, if we evaluate what remains, this can be rewritten like this, G K S ds, and we have shown that here that has to evaluate the 1. So basically, this whole expression collapses into the non-delayed version. So that is great, because then we can just take over the already existing expression for non-delayed systems with non-mass action kinetics from the Vagi paper from 2024, and that will be perfectly applicable to us, for us as well. So here we have that in implicit and explicit form. Just leave it here for now. We'll come back to it in a sec. And Gabor has been talking about stoichiometric compatibility classes as well. So we have this functional CV for a given vector v, and well, this is if we would drop the time delay, then this, and we would assume some kind of weight conservation law, then we could find a v that would be just a vector of molecular weights in like a chemical system. But of course, this doesn't have to. I mean, our system class doesn't have to obey these rules. This was just a side comment. So we have something like this, and then 2 states are in the same stoichiometric compatibility class if this expression in the middle holds. So if this functional evaluates to the same value for each and every v vector taken from the orthogonal complement to the stoichiometric subspace. Yeah, and then if we just take this over to the other side, then the right-hand side will be 0, and then we will have something in the form of v transposed times basically the bracketed phrase evaluated for what do we have here, psi and phi. Okay, and this will be equal to 0, and since we have a vector product that is equals to 0, then it follows that whatever we have here, this has to be in the stoichiometric subspace, yeah, in S. We'll come back here as well. We'll need this later. So the next question is, how do we prove the existence of equilibrium in each and every compatibility class? Well, mathematically, we just take the definitions of the set of equilibria and the set of and the characterization of compatibility classes for each and every phi. So this is like any compatibility class, and yeah, we try to take the intersection, and we prove that that intersection is non-empty. So to be able to do that, we will need an auxiliary lemma, on which we will rely. This we have almost taken over from the LibTech paper from 2019, except in the LibTech paper they have had distributed delay, but mass section kinetics, I think. And since we have non-mass section kinetics, we have these gamma functions. We had to adopt the lemma, but that wasn't that big of a deal because, okay, so just in a few moments, I would like to give a brief overview how they prove this. So they have this expression, and they have constructed an f function so that its gradient is this expression, and then they have shown that as f that as axes go to infinity, f also evaluates to infinity. So it's like it's an outward growing function. And then they have shown that if you take the set of all the points that evaluate to that are equal to or lower than f evaluated at 0, that is a non-empty compact set. And because it's a compact set, f must take a minimum inside of that set as a minimum. And because it's a minimum, and since we are considering only v's in v perp, then the directional derivative in this direction must be 0, so the gradient must lie in v. Okay, so this is how it works, and we could almost entirely take this over. We have this gamma function that is strictly increasing, that doesn't break this. We have, sorry, more like here, we have the inverse of this gamma function, but because of the inverse function theorem, the inverse will be also strictly increasing, so none of this breaks. so we have this lemma that we'll be using. So let's not forget where we were. We were trying to prove that there's at least one equilibrium point inside each compatibility class. So we said that we would put the characterizations into each other. So here it is, and I left our lemma, or like our take on the lemma here, so that later I can reference it. Okay, so I just rearrange it a little bit. I just took this to the end, and I decompose this sum into 2 parts, and then we evaluated the inner integral because that has no u in it. That will eventually just evaluate to minus s, and whatever we have here, that is just a constant, so that it can be it can be factored out. So we end up with something like this, and here basically everything has a pair in the lemma, and that is a bit hard to see, I think. So I colored in everything. So yeah, and the lemma said that's not written here anymore because of space reasons, but the lemma said that there should exist V in V perp if this is fulfilled. So that means that there should exist a V in S perp in this case, and that is great because if we go back to the characterization of the equilibria, that is what we need. So hence, it has been proven that we have at least one equilibrium in each and every compatibility class. Then the next task was proving uniqueness of equilibria. Okay, so here we because here we have uniqueness. So this was an inverse. This was an inverse proof. We basically take two states. We postulated there are two equilibria that are not equal to each other, and just prove that cannot be. So here on the left-hand side, we have the implicit formation of the equilibria. Okay, and on the right-hand side, we have the characterization of the compatibility class again for these 2 points. And I think we remember this, that this must reside in S perp. This must reside in S. So if you take the vector product, because they're perpendicular to each other, this must be 0. Okay, so then we rely on two little tools here. One of those being this one here, ln A minus ln B times A minus B. That is greater than 0 if A is not equal to B, basically, and we use that here and here as well. Okay, and we have this other remaining part here, and here again we just evaluate the inner integral. That will be minus S. So basically we have this integral here then, and that will be greater than 0, because if we wouldn't have this minus S here, then from before that would evaluate to 1. Okay, maybe I don't have to do this all the time. Yeah, this evaluates to 1, and because minus S is strictly positive over this range, minus tau to 0. Also because GS, just integral GS evaluates to 1, this means that G cannot be identically 0. And because minus S is also strictly positive, this has to be greater than 0. So with that, this is only ever 0 if A equals B. So with that, we have proven that this equilibrium is also unique. Okay, and what remains is Lyapunov stability. And here again, we just adopted the Lyapunov-Krasovsky function from the Baghi paper. We had to add the distributed delay, of course. Yeah, and then we just took the time derivative and tried to show that that is less than or equal to 0. Hence, we have Lyapunov stability. Because for that, we introduced this shorthand, and one might ask, why do we have? So I think Gabor also pointed out that in the first the first summation is over the species, the number of species, and if the number of species is a summation over species, and the second summation is over reactions. And so one might ask, okay, so where did n go when we differentiated? It's not here anymore, but this is also not a constant, because we have psi here, and we have this here, so this cannot be a constant. Yeah, indeed. What happens is that because if we, let's say for psi we input xt, then basically what we have here is the current state, and because of the fundamental theorem of calculus and chain rule, this part, if it differentiates, let's call it v dot 1, this will just become this butterscotch colored term times the derivative of x xi, yeah, and that the derivative of x, that is just the original ODE or DDE, I should have said, from here, and this is a summation over reactions here in it. So this is how we got rid of that. Okay, so we have that. Then we just collect the integrals up until here. Then we use a little tool again here, which is that e to the a times b minus a, that's less than or equal to a to the b minus a to the a, okay? And that is something that we can apply to here. So this blue part would be a in this expression. Also, yeah, because we already know that this evaluates to 1. We can essentially get rid of that. This part here, that is just extracted from here, and because this is an integration over s, this is an integration in regards to s, and this has no s in it. This is just a constant, so it can be taken over. That's how we got this whole, I should have done this. That's how we got this whole phrase. And okay, so basically the green part cancels out the this part, so this whole row falls away. Okay. So here we have this rewritten according to this rule here, and that is great because now we can cancel out these terms. These are exactly the terms that have had s's in them, and this is an integration over s. So whatever remains in here, that is considered a constant from the point of view of this integral. And also, sorry, I might have not been super transparent about, I have to hurry up a little bit as well, super transparent about that so this is what we got from here, and because of this we could, because of this inequality, we could introduce this inequality here, this inequality sign here. So this is like an upper bound that we have introduced. So then, as I said, whatever remains in the integral can be factored out. This is what we did here. This is the good old evaluating this function to 1. I always want to say distribution function, but I just a brain freeze here. What is this? Okay, okay, eventually I'll recall. Okay, so this falls out. And then what we do is here we have summation over all the reactions, and this is just a change of notation. We say, okay, summing over all the reactions is the same as summing over all the complexes, and for each complex, we're going over all the complexes, and for each complex we are summing over all the reactions that for which that complex is the source. We're still counting the same things, just from a different viewpoint. So here we have a switch in notation or viewpoint. And one important thing that will be used on the next slide. Here we have Q prime. And Q prime had Y prime in it. Y prime is the target stoichiometric vector. And I would just like to point out here that basically, if we have the target stoichiometric vector of a reaction of anything to a complex C, that is basically just the chemical composition of C, right? Because whenever we have something, and we'll have C. So that is the target. So that is just the composition of C, and that is the same as the source stoichiometric vector of a reaction that creates from C something. Okay, so because of this, because this is how we'll get rid of this prime here on the next slide, exactly here. Yeah. And okay, we also decompose this sum into two. But more importantly, here we change the we switch the way we look at the reactions. So we will no longer be summing over all of the complexes, outgoing reactions, so to say, but on all of the complexes, incoming reactions, but it's still the same. At the end, we still are counting the same things. It's the same. So we do this. Okay, now we have in both sums, and I will be done in a few minutes. I'll promise. So this one, sorry. So this thing here and this expression here are the same, and because this only depends on C, because again, this is just this basically depends on the chemical composition or on what species build up C. This is what it depends on. This does not depend on the actual reaction. We can factor this out from the inner sums. So that's why it has been factored out here. And basically at this point we are done, because what remains here inside of the parentheses, this is basically just this thing here rearranged. And what that means is, this is a definition of complex balancing. So the rate of creation of each complex equals its rate of annihilation So the sum of rates of reactions leading to the complex is equal to the sum of rates of reactions leading from it. This is what that is mathematically, and this because we know that we are in a complex balance system that has to be 0. So that is indeed so. This term basically brings everything here to 0, and because earlier we had this less than or equal sign. We have Lyapunov stability, and just very quickly, I rushed through the examples here. So this first one is a reversible reaction. On the reverse reaction, we have a time delay as well. This is like a uniform delay, and the transformation, the gamma function is this. It's like an approximation of a step function, not an actual step function. So that it remains continuous, but something very close to it. And this is to show. This is just to check how the system behaves if we have a gamma that is not everywhere differentiable. And it seems to be seems not to be a problem. So we have the colorful trajectories here. They're just trajectories starting from different states. All of the starting states are considered like with constant history functions. The dashed lines are the compatibility classes. And here, this little part is so here it is zoomed in plus some extra curves added, because here with orange we have the non-mass action system with a discrete delay, and this is a discrete delay that is the same as the mean of the delay distribution, so this dotted line, basically. And the question might arise: do they actually? Is this like a fluke, or do they actually converge to the same equilibrium? And the answer is if the delay distribution is is like this. I might have said normal before, so what I meant is uniform. Sorry. If the delay distribution is uniform, then yes. Otherwise, this is not generally true. But here, yes. Here we have the non-delayed system. The dashed lines, these dotted lines are the equilibria set. The black one is for the non-mass action system. The magenta one is for the mass action system. So this is how it looks like. And we also have had another little example. It's like an enzyme kinetic type thing with this Michaelis-Menten type rate functions. And also here we have a delay distribution that is skewed, and here are the time plots. So at this point, I would like to thank you for your attention, and I believe we are here to answer your questions.